Very good morning. I am Dr. Ganesha Balamurugan, Assistant Professor, Department of Mechanical Engineering from IFIT Engineering College. I am very glad to present the GATE coachings for strength of materials. So I am very proud to present this presentation for our students because nowadays GATE is mandatory for every aspect in India. Even it has a valid score and valid respectful meaning even at the abroad, right? Many universities abroad are considering the GATE scores. And in PSUs in India, many PSUs and other things are recruiting based upon the GATE score. Even you can go for higher studies in NITs, IITs, and IISc based upon the GATE scores. So even for PhD also nowadays they are considering to recruit based upon the GATE score. So if you are well versed in the GATE syllabus, most probably in the mechanical engineering student, I will say, if you are well versed in the GATE syllabus, then you will be crack any type of technical entrance exams happening everywhere in India. Most probably in Tamil Nadu, many government sectors are conducting many variety of exams, and they are mostly they will be based upon the GATE syllabus. And if you complete the MTech, and TRB is the Teacher Recruitment Board, and to get the permanent job in the technical engineering positions in the government colleges. So you can easily crack these TRB if you are well versed and very experienced in this GATE, right? So it is now, I hope it can be each and every undergraduate student should train yourself to crack the GATE in such a way that, so first of all, you try to crack the GATE. So you can achieving the highest mark is secondary. You can focus on it, no problem. You can focus for the highest marks, but you have to crack first. You have to crack the GATE. So it will be the first step, and you will be get recognized everywhere, right? Then you can able to upgrade yourself to get highest ranks in the GATE. So and it most probably, if you are started preparation for the GATE, you will find the another dimension of engineering. What you have studied in the 4 years will be sufficient, but also not sufficient. So the way, the approach of learning the GATE, learning for the GATE is entirely will open the new paradigm for engineering, mechanical engineering, whatever engineering. So you will learn more deeply. You can it lead to more deep concern about the particular field. So here I have started about starting this course on the strength of materials. This course has different names. So somebody will call this as strength of materials, and somebody will call them as mechanics of materials, mechanics of solids, mechanics of deformable solids, and mechanics of deformable materials. Many names we can give for this subject. So here I'm very convenient and very comfortable with the term strength of materials. So we are analyzing and we are learning to analyze the strength of different materials under different loading conditions. The prerequisite for this course, strength of material, is engineering mechanics. So if you know how to find the forces and the reactions, and if you have some basic knowledge in the engineering mechanics, then this strength of material course will be very easy for you to understand it. So engineering mechanics is prerequisite and very, very fundamental of this course, right? So let's start this gate. And first of all, I'm starting with the basics, because without understanding the basics of the terms, you cannot be able to solve the problems. So very slowly, I'm introducing about, starting with the basics, and we will discuss the gate problems. Okay, in subsequent lectures, we can discuss different gate problems. We will solve different gate problems of strength of materials, and we will get expertise in this field, right? So I welcome to this course of GATE training for strength of materials, and let's start the session. Yeah, this is the, one second. So first, the basic, I already told you, the basic of the strength of material is mechanics, that is engineering mechanics. So there are three branches are evolving from the engineering mechanics. One is mechanics of rigid bodies, and mechanics of solids, and mechanics of fluids. Okay, then mostly in the most of the, all the engineering students will study most probably all mechanical engineering students. They will study about the engineering mechanics. In the engineering mechanics are this here, this mechanics of rigid bodies. So here you are studying, you are studying how these structures, different structures are experiencing different loads, and without we are analyzing the reactions of the application of the forces, right? So we will see the different forces in this subsequent lecture, right? And you are studying about how to apply the forces and how these forces are creating the reaction, different reaction at the different fixed points, right? And based upon that, you can study about the kinematics and dynamics also along with this, right? And there you will never consider about the deformation about those structures. So you are assuming that all the structures are not deformed, and this is why the name emerged as rigid bodies, mechanics of rigid bodies. And these mechanics of rigid body is the basic. So understand the forces, right? Understand the forces, how these forces are acting, and how we have to find out the reaction for these forces, right? So then if you identify the subsequent reactions, corresponding reactions, then we will easily do some calculations, and we can switch over to the mechanics of solids. So what is mechanics of solids? It's nothing but the course of strength of materials or mechanics of materials. Here we are considering about the strength of material. That is why I'm saying I'm comfortable with this term, strength of materials. Now we are analyzing the strength of each material structures, not only materials. So materials in the form of structures, different structures, beams, columns, and circular shafts, and different structures. And these structures, how they are experiencing different loads. Loads means forces, and based upon the forces, how they are deforming. Okay, what is reaction? So in the previous engineering mechanics of rigid bodies, we'll learn to find out the reactions of each action of forces. So in these mechanics of solids, we are analyzing how these reactions are responsible for the deformation of particular structures, right? So now this is the strength of materials, where we are coming with the terms stress and strains and deformation, right? Most of these, everything, strength of materials is comprising with the two terms, stress and strains and load, right? And mechanics of fluids. Mechanics of fluids is fully studied about, completely studying about the different movements, kinematics and dynamics of fluids, and gases and liquids. So now we are not concerning about this mechanics of fluids. So now we will start with this strength of materials only. This is the content of this course. Otherwise, you can say the syllabus of this course. Introduction to stress and general state of stress, and introduction to strain, material properties, torsion in circular shafts, shear forces and bending moments, bending and shear stresses in beams, columns, complex stress and strain, and pressure vessels. So these are the syllabus for this course, and most of the gate problems are are arrived through this syllabus, all these contents. Okay, so we will see one by one, and we will see one by one basics of each and every content, and we will see the problems, gate problems of each content, and we will solve the problems, and we will get well versed in these particular problems, and we will build the confidence to face the gate exam. If you find after completion of this course, I hope and I promise you, after completion of this course, you will very confidently face the gate mechanical engineering syllabus, and you will confidently attempt the length of material questions, right? So introduction to stress. So what is this stress? It is the measure of internal resistance of the body against the external load. So here we are learning in the mechanics of rigid bodies. We have learning a number of reactions for the action of forces. These reactions, while applying any force on any structure, it will the force will depends upon the magnitude of the force. It will try to change the dimension. So this change in dimension will be termed as deformation. But at the same time, the material will resist for this deformation or change in dimension, and it will offer this resistance. And this resistance is called stress. So it is experiencing some stress, right? So like our human, okay, we are also experiencing stress. If any other tension or any other external things happening over it, and we will internally, our mind and psychologically, we are giving the resistance for the breakdown, and during this process we will experience the stress. The same thing is happening in the material also. The material always try to stay in the existing condition or dimension. So when the external, it always resisting for the change. Okay, so for that resistance of change is called stress. So sorry, mathematically we can represent as the force acting per unit unit area. This is stress, right? So how much of force, because we are applying the external force, but without applying the force, what is the need of the material to offer the resistance for the change? So we are applying the force per unit area, in particular area, square area, mm square or centimeter square. So what will be this thing happen? This stresses happen, and this is the sigma, the representation. So sigma is the force by area. So this is the mathematical representation of this stress. So for example, and the unit. So what is the unit of this? Unit generally we can give as Newton per meter square, that is in pascals, and another Newton per mm square, that is megapascal. So Newton per mm square is higher when compared to the Newton per meter square, because Newton per meter square is and the Pascal, and if the magnitude is 10 to the power of 6 times means, So then it is megapascal. If it is megapascal, then we can directly mention it as a Newton per mm square, right? So this is the thing. And most probably, so different, I'm telling you one thing. So I am trying to explain you, please wait. So this is this unit, and this unit, no, this representation, force by area is for uniform stress. There are three different type of stresses are there. Okay, so what are these different type of stresses? So three forms of stress, three forms of stress. One is, I will write like this here. Uniform stress, linear stress, parabolic stress. So now these three forms of stress are available, and this representation is matching only with the uniform stress. And for linear stress, it involves the linear equation, and parabolic stress, it involves the parabolic equation. So this uniform stress, right? So how we can represent this uniform stress? One second. So consider here, this is the block, and if you are applying some forces in this block, okay, so I will change the color for your easy understanding. And this is the block, and if you are applying the forces here like this, so a force like this, okay, and how we can represent the force? The force we can represent as P, okay. So we are applying the force like this in this end, and this is the cross section. Okay, if you cut this here, you cut this here, this is the total. This is the cross section, and it will experience a change here, experience a resistance here. Okay. The same, this type of resistance here. Now you can see. One second, please. You can see these are the different reactions for this action of force, and this is the cross section. Okay, another half section will be there here. Okay, so if you cut the cross section, we will see this type of forces, that is reactions. If all the reactions are pointing towards the same target, okay, same point, all the reaction forces are pointing the same point, are uniform, all the reaction magnitudes are uniform, then they are called uniform stresses. Okay, and this representation sigma is equal to force by area is most only suitable for these uniform stresses. right? And another, so if you, example for this I'm taking, again the forces are varying here. So there is a variation in the forces. There is no uniform magnitude in the forces. Some force like this, there is a variation in the forces, right? Like this, some variation in positive direction, in negative direction. So like this, some variation in the forces, even the positive direction also, the variation in the magnitude of the forces, so will create a different approach over it. So we cannot, this is linear. So this is the linear. So this is called the linear stresses, and to represent these linear stresses, you have to generate a linear equation. And to solve these linear stresses, we cannot apply this formula, sigma equal to force by area, we cannot apply it, right? And if the forces are parabolic, and they are changing with the parabolic, and their magnitudes are varying like a parabolic. So I will explain you here. And if you draw some parabolic like these curves, so I'm making a circle, but it will be a parabolic, right? Okay, this is parabolic. So the variation in the forces, like the variation of magnitude in the forces in the parabolic, like parabolic, these are the parabolic stresses. And solve these stresses, stress problems, you have to write the parabolic equation, have to create a parabolic equation to solve these problems. And here you should not apply this representation of sigma, the force by area. Only the sigma force by area is only applicable for uniform stresses. Okay, that is all the magnitude of this resistance force are equal, should be equal in a particular square area, right? Most probably we are considering these uniform stresses in the strength of material, and we will understand how these uniform stresses will create different deformations, and we have to find out the values for these deformations. Okay, so these linear stresses and parabolic stresses we are never going to consider in this strength of material course, even your UG and for this GATE course also. So here, how these stresses are generating? By application of load only, these stresses are generating. So the stress depends upon the deformation, I already told you, and the deformation. If the deformation is uniform, the stresses are uniform. If the deformations are not uniform, the stresses are not uniform. That is why we are considering, we are grouping the stresses as uniform stress, linear stress, and parabolic stress like that, right? Now, based upon the loading condition, that is application of forces, okay, of loading condition, the stresses will vary, right? Here we can group here. If you understand this concept, then it will be more helpful for solving all the problems in this strength of materials, right? So now we can group these loads into two categories. One is force, and another one is moment. Okay, so you can ask, then what is the you have saying force which is equal to load. So that way of application of that force will have, we can change the name into force and momentum. Moment, not momentum, moment, right? So the way that particular force is acting on the structures. So depends upon that, we are grouping these or we are categorizing these as force and moment. So force, again, we can subdivide it into axial forces and transverse forces, right? And moment. And moment means, I will explain you, right? And clearly. And this moment can be again subdivided into bending and twisting. So these variations. So in the next slide, we can see we can correlate these loads into stresses. So loads are stresses are creating due to the application of these loads. So there are direct stress and indirect stress, okay? Direct and indirect stress. So direct stress are created by the force, okay? That is force type of loads, and indirect stresses are created by moment type of loads, right? And here again we are already seen this axial forces are subdivided into axial and transverse. Now you can see these axial forces will create axial stresses. Mostly these axial stresses are like tensile and compressive stresses, and transverse type of forces create shear stresses, right? And bending. This moment type of flow, that is indirect stresses, right? That which are creating indirect stresses. This moment then create bending, and this bending moment will create bending stress in the structures. Mostly in the beam type of problems, you will beams and column type of problems, you will mostly experience this type of bending moment and this bending stresses, okay? And twisting type of moment will create torsional stresses, mostly the shaft, circular type of shafts, rectangular shafts, and these rotating shafts in a particular RPM are fixed at one end or attached to one end and transmitting the power. This type of shafts will experience this twisting moment and they will experience the torsional stresses, right? So I will explain you here each and everything now. Now I will explain you about this the type of forces. Okay, 1 second. So now we consider this is one structure, right? And we are applying the forces in their axial direction, in this axial direction. And these are the axes, okay? And these are the axes. So this orange line is because mostly as per the engineering drawing or machine drawing standard, this axis should be mentioned in a dotted line, okay, or segmented line. But because of the limitation here, I'm showing these axes as the orange line for showing the difference between the structure and the axis. And the forces, means red color arrow marks, are called the forces. They are applying along the direction of this axis, right? And it will create, and it will try to change or to try to deform the material in the axial direction, an axial way, okay? Most probably, if it is a cylindrical specimen, means it will reduce the diameter, or if a circular, means it will try to change the cross section. So these are the axial forces. I'm telling about the forces, not stresses, okay? So I'm explaining about axial force. This is axial force, right? And what is meant by transverse force? So again, we will see with the same example and the same structure. Okay, they assume this is same structure, and I'm applying the load like this. So I will change the color of that load now this time for your understanding. I'm applying the load like this, and this is the direction, and this is the axis. Assume this is the axis which is passing at the center. And because of I'm applying the load here, which are perpendicular to the axis. Previously in the axial forces, I'm applying along the axis, applying the forces along the axis. Here, I'm applying the force perpendicular to the axis, okay? And I will get the reaction like this. I will get the reaction like this at this end. And similarly at this end also I'm getting the reaction. Okay. And these are called, and these type of forces are called transverse force. And these transverse force will create shear stresses. Okay. So in one section, because we are applying the load in this center, and reaction is occurring at this edge, and it will create one shear value, that is shearing. So cutting out that material into half, trying to cutting out into material into half, that is called shearing, right? And here mostly the axial forces will responsible for creating. Now this indication is pulling direction, right? This is pulling direction along the axis. So this pulling direction of this axial force will create tensile stresses, right? Tensile stresses. If the direction of the arrow mark will change and it is in the pushing nature, and it will create the compressive stresses. Okay, mostly here these transverse forces will create shear stresses, right? And now we'll switch over to moments. So what are moments? I will explain you. So now assume this is one beam, a circular beam or a rectangular beam, whatever may be. So I'm fixing at this end. So for representation of fixing, this I have to show like this. Then only it is understood that this particular edge is fixed. Okay, this particular edge is fixed, and I will draw this axis of it. And this is the axis, the orange line is axis, and I'm applying the load. So I'll mark it as black along the axis. Along the axis. And applying, now we will discussing about the moment. Actually, what will happen? This moment, if I applying load like this, mostly what will happen, the material will extend along the direction. Okay, try to change the dimension along the direction, right? Then it will be the forces. This application of load is forces, and it will be the tensile deformation, or maybe a compressive deformation. But Assume this here. Another example I will tell you. So this may be another structure, and I am fixing this edge here. Please. I'm fixing the edge here. Okay, and axis will be here like this. So this is the axis, but the application of load is here in this edge. The arrow mark is the load, and these black lines, these structures, black blocks are structures, and this orange line is axis. These loads are not applied along the axis, and they are not perpendicular to the axis also. That also you have to mention. You can ask in previously the transverse loads are not applied along the axis, but they are applied perpendicular to the axis. But they are directly, these forces in previously the force type of loads directly making impact. They are directly applied on the axis. It may be along the axis or perpendicular to the axis. All the effects of the load are along the on the axis. Okay, so all the effects of the load on the axis. So maybe it may be along the axis, or it may be perpendicular to the axis. But here in this moment, how moment is created, now you can see there is a wide variation. A wide variation. I will give in this different color. So this distance, right, from the axis up to some distance, the force is applied. It is not applied along the axis, not on the axis, not on the axis. Maybe that you have to understand very clearly. That is a difference between force and moment. Okay, the force, the loads are applied on the axis. It may be along the axis or perpendicular to the axis. But here in the moment, they are not acted on the axis. It is some distance away from the axis, they are acting. So this is the distance away from the axis, they are acting. And what will happen, it will create, this is the moment it will create. Maybe this distance, okay, this distance is D. This distance D. So this force P, this force is P. And this, how we can write this moment, which is equal to P into D, Newton meter moment. The force into distance, that is unit of this moment is Newton into meter. It will create different type of stresses. This moment that is not acting along the axis, and they are not, that is not along perpendicular to the axis. In simply, I can tell these forces are, this is not force, I cannot use the term force. These loads are not actually acting on the axis, but away from the axis, from the distance, and it will create some, this is called moment. And these it will tend to rotate the this structure, or this type of force loads will tend to bend the structures. Okay, so bend the structures, it will create these moments can be calculated, mostly calculated by force into distance, that is Newton meter. So these type of loads will responsible for bending and twisting and these stresses, bending stresses and the twisting stresses, that is torsional stresses, are these type of forces are responsible for that. So the low these moment a moment responsible for bending of the structures are bending moments, and these loads responsible or moments responsible for twisting of the structure are called twisting moments. And the stresses caused by this bending moment are bending stresses, and stress caused by the twisting moment are torsional stresses. Okay, if you take the cross section, the cross section means what? So if I take this cross section, so I'm cutting this half of this portion. Okay, if I am cutting the half of this portion, and if representing here this, for example, I'm assuming this is a cylindrical rod. So cylindrical rod means this is the cylindrical rod, and this is the cross section. If you cut this in this perpendicular direction, and if you see this cut out portion means this is the cross section, cylindrical rod. So we can make it into 3 axes. So one axis, sorry. So this one axis, and this is one axis, and these are one axis. Okay, and this is y direction, y, and this is x, and this is z, that is z. Right. So these are the 3 directions we are assuming. That is x direction in the right and left, and y direction in the up and down, and z there is pointing towards you. Okay, this is y, and this is x, and this is z direction, z direction. And if you are making the turning, so we are making some moment here in this direction, right? So how to apply this moment? So we're making to rotate. And making to rotate. And making to rotate in this direction. So here this is, for example, these axes, y-axis and x-axis are parallel axes. Okay, they are parallel to the cross section. Now forget about the axis, this axis. Okay, now it is a plane. Consider this is a plane. Cross section as a plane, and for this plane, and this x-axis and y-axis are parallel to the plane, and z-axis is perpendicular to the plane. That is, so this is, for example, this is parallel, and this is parallel, and this is perpendicular. So now you can seeing my fingers towards you. So for me, again it is perpendicular, so it's projecting out. Okay, so I'm applying the moment here in x direction moment, and y direction moment, and z direction moment. So the moment they are they're, that is acting. Wait. So the moments are responsible. The moment they are responsible for parallel axes. Parallel axes are called bending moment. So this bending moment, okay. For example, I can tell here. This is X. So okay. So this X. So this direction is X and this direction is Y, and perpendicular to this cross section is Z, right? So these moments. So for in this representation, how we represent this one, this axis. For example, I'm telling here, this is X, this is Y, and this is Z. In this view of representation, the front view of for example, this is the front view of representation. This is X, this is Y, and this is Z, right? So if you take the cross section here, you can see this cross sectional plane. Then you can imagine that this is Y and this is X, and perpendicular to this plane is Z, right? And now you can see this twisting, any moment applying on the Z direction are responsible for twisting. It will create some twisting effect, and these are called these are called the torsional stresses or twisting moment, and this twisting moment will create the torsional stresses. Okay, for example, you assume that you have to assume, okay, I'm taking this pen, assume this pen, and this is Z direction. Okay, this is Z direction, and this is Y direction, and this is X direction in the front view. Okay, and if I'm taking cross section like this, if you're taking cross section of this, and this is the cross section. Okay, this is the cross section. Now you can sorry. So now this cross section, this is cross section, this is Y direction, and this is X direction, and the thing you are facing this is Z direction. This is Z direction. Okay, X direction, Y direction, Z direction. That you have to. This is for cross section plane, but for front view, this is X, and this is Y, and this is X. Okay, if I applying any moment in this Z direction, this whole structure will twist like this, and this is called torsional effect. Okay, torsional. This is called torsional. This twisting moment is called torsional. This will create the torsional stresses along the cross section. If I try to rotate in the Y direction, this is one type of bending. This is not torsional. This is bending. One type of bending along the Y direction. And if I trying to rotate in the X direction, so Y direction means this is Y direction. Okay, this is Y direction, and this is the pure bending. You can be able to see. So if I am trying to rotate in the Y direction, then it will create a bending. This is one bending, and this is also bending along the. I am trying to rotate the structure in the X direction, and this is called X-axis bending. These effects are bending. That is, moment occurring at the Y axis and X axis are called bending, and the moment acting on the Z direction is called twisting moment, and they will create torsional stresses. And the moments they are causing on the Y and the X, they are called bending, and they will cause bending stresses. Okay, so that you have to remember in your mind. So whatever machine design and other synth of material problems, if you understand this basic concept, you can easily solve the problem. Okay, students. So thank you. Now I will conclude this session. In the next section, we will see in detail about different forms of stresses and how to solve the problems in the stresses, right? Thank you very much.